Yes. In last video, we get the idea about what you mean by collapse load, okay, and what you mean by load factor and all these conditions. So in this video, directly we go to the numericals about find out the expression for collapse load. For a simply supported beam, have point load at the center. Okay, by using kinematic method and also static method, we can get the solution for this. So I am going to start with a example directly. So find out the expression, right? Find out the expression for collapse load for a simply supported member subjected to point load at the middle. This is simply supported member. The point load is subjected to at the middle. So middle in the sense span is divided by 2. So then this is AB end. Then for this we know that we have to identify the bending moment diagram for this condition. Okay, I am going to draw the bending moment diagram for this. So maximum bending moment diagram is like this, right? So this is the maximum bending moment diagram is occurs. So what is the value of this? Okay, this one is WC into L divided by 4 as of now. So then by using static method, the first method is static method I am going to follow. Okay, the static method. In the static method we have to identify, or we know that the total bending moment at any point which is equals to total plastic moment at that point. Okay, the static total bending moment. Okay, total bending moment at any point which is equals to total plastic moment, total plastic moment at that point, in the sense where we are having the maximum bending moment or total bending moment, where we are getting where in the sense any point. Okay, at that point what is the total plastic moment is there, we are going to compare those two. So in this total bending moment, we know that that is WCL by 4. So WCL divided by 4 we can take, so which is equals to total plastic moment in the sense, so how many plastic hinges are developed in this. Okay, this is simply supported member. We are having 7 to 8 plastic hinges locations points. So when we are having fixity, that point is also a plastic hinge. So when we are having intermediate support, that is the one. And where we are changing the geometry or cross section of the member, so that is also a plastic hinge which developed. So like this we are having, so where we are having the maximum bending moment and where we are having the or under the point load we are getting the maximum bending moment. Okay, also plastic hinge is developed under the point load, so only one is possible plastic hinges. So in this point, this is the exterior support, also this is the exterior support, so there is no development of plastic hinges, only the development of plastic hinges at the under the point load, or where we are having the maximum bending moment, that is only one, that is MP. So by simplifying or equating equations, so WC which is equals to MP divided by L into 4, or 4 MP by L. So this is the by collapse load or expression of collapse load by using static method. And also by using kinematic method we can identify. So the second method, that is a kinematic method. Okay, in kinematic method, so we know that so external work done which is equals to internal work done. Okay, so what principle of virtual work. Okay, that is external work done which is equals to internal work done. So in the external work done, in the sense what, the force into displacement. Okay, so force into displacement we are going to consider. So that is the external work done. Okay, then similarly internal work done in the sense moment into rotation, moment into rotation. What is stiffness? We know that the load is required to produce unit displacement. Okay, the force is required to produce unit displacement. That is the external work done. Okay, how much force is required to unit displacement. So like that, so external work done which is equals to internal work done. So external work done in the sense force into displacement. Okay, so what is the force here? Okay, so in the next slide we can write, so this is the loading or given the loading condition, so that is WC. So right, for this point, so this is the longitudinal axis. After application of the load, the plastic condition is behaves, or this is the plastic analysis diagram. I want to write this is considered as the rotations. Okay, rotation at point A and rotation at point B. Okay, this is a A end, this is a B end. So there is no changes in theta A and theta B. So because of the load is acting in the middle, so there is no slopes is differ. So theta A equals to theta B equals to theta. We can consider like this. So this is the maximum displacement for this collapse load. Okay, so delta. So this length is L by 2 and this length is L by 2. Okay, so we are going to identify the what is the value of delta, and for this is the opposite angles and this is also opposite angle. Okay, so this is theta and this also theta. Okay, theta A equals to theta, we can consider theta B equals to theta. So opposite angles are equal. So then where we are having the maximum bending moment, or where we are having the, or under the point load, we'll get the plastic hinges. Okay, so that's why I'm going to write this is the plastic hinges. Okay, MP theta and MP theta we can get. So external work done. Before going to that, so what is the value of delta? How we are going to get the delta value? So yes, so consider the triangle, half triangle. So consider this half triangle. So we'll get so delta. So this is L by 2, this is the delta value. Okay, so we are going to apply the tan theta. So this is the theta, so tan theta equals to opposite by adjacent side. So then, okay, theta is very small compared to the whole structure, so theta equals tan theta is get converted into theta. Okay, delta divided by L by 2. So delta we required, so delta in the sense what, theta into L divided by 2, right? So this is a condition. So load is WC. Okay, so displacement is delta. Okay, so external work done which is equals to load into displacement, we know that. Okay, load into displacement. Okay, so load is WC, the displacement is delta. So delta we know that, that is theta L by 2. So WC into theta into L divided by 2. Okay, so this is the left hand side. Okay, we also identify the right hand side, that is internal work done. Internal work done in the sense moment into rotation. Okay, moment into, that is what, which moment? It's a plastic moment. Moment into rotation. So plastic, how many plastic moments are there? 2 plastic moments are there. Okay, rotation is respective rotations. This is a MP theta and this is a MP theta. So 2 MP theta we can write. Okay, equating both the equations, left and right hand side equation, WE equals to WI, external work done equals to internal work done. So WC into theta L divided by 2, which is equals to 2 MP theta. Okay, so then we require WC value. So WC which is equals to, okay, so in this equation theta get cancelled. Okay, so 2 by L, 2 by L, okay, 2 divided by L into 2 MP. Okay, 2 into 2, 4 MP by L. Okay, this is our collapse load by using kinematic method, 4 MP by L. So in the previous slide, by using static method 4 MP by L, and by using kinematic method 4 MP by L. Like this we can find out the expression for collapse load. Okay, so for this is a very simple method or to identify the collapse load. Okay, so in the next slide we'll get the one more problem related to plastic and the collapse load. So thank you.